way you don't forget. I have done it many, many times. I type up the entire command line and just go like, well, when it's time, I'm going to press the enter key, and never got to press the enter key.
In all the classes I've taken with you, I don't think I've ever, have you, are there any open source projects that you've contributed to, or?
I used to post one, open source project, but
The squid thing?
Huh?
Was it the squid thing?
Was it a
Squid? I think you were using squid.
Yeah, I did some work with Squid as well, but the open source project that I posted was really for a co-fire, a Motorola co-fire processor, and I wrote the GDB backend without an operating system. So if you develop a single board computer using a co-fire processor and you don't throw in enough RAM to run actually Linux and stuff like that, it will still work. So it's a very minimal firmware so that the controller can talk to GDB on the other side. So it can load programs, it can debug and stuff like that, but you don't need an operating system to do it. So it's a very, very lightweight
what would you write it in?
Assembly.
I was about to say, that sounds like an assembly project, yeah.
Yeah, so the whole communication protocol, it was all done pretty much in assembly.
How many lines would you say?
I don't remember. I also wrote an actual real-time operating system for the Atmel AVR line of processor. In assembly. Yeah. Well, the footprint of the entire kernel is only 2 kilobytes.
Yeah, which is actually
But those devices only have, the smaller of those devices only have 8 to 32 kilobytes of code space. So you need the operating system to have a very tiny footprint. And by writing it in assembly and just be clever about the entry points and exit points of functions, I ended up saving quite a bit of space. So that's kind of cool. All right. Well, it is 9:01. I am going to get started. Are there any questions about the 2 homework assignments that you have to? Yep, go ahead.
So for the one with the tar, well, I opened up the zip and I saw that was like home user and a bunch of user data.
That means you might not have entered. Okay, are you how many files do you have in the tarball?
2. Checked out PLN, checked out.
That's fine, but the path is long because it is starting from the root directory.
Right. Is that how it's supposed to be?
That's how it's supposed to be. So you're good.
So does it matter that I did it on my native machine instead of the VirtualBox?
Nope. For this assignment, it should not really matter.
Okay, so it doesn't matter what home/super.
That's correct. Because for this homework assignment, we are not actually running any type of executable in binary, and as a result, you can run it on a Raspberry Pi and it will still work. Not that I want you guys to run it on a Raspberry Pi, but if you did, it would still be okay. Yep.
For the Logisim assignment, what did you want to name?
For the Logisim, you can name it any way you want. I did not write down exactly how I want you to name it. So if I don't say, you have the freedom to rename it.
Oh, that's dangerous. I have a history of naming things weird.
Well, same here. We all have a little systematic way of naming things. All right, so what we'll do today is, this is wrong class. 362 is mobile programming. It's fun, but it's not the right class. All right, so let's move on to 310, and I'll double check the recorder just to make sure that it is recording from the right channel. Okay, all right, so there we go. So what we are going to focus on today is how to add numbers. Yes, you heard me right. I'm gonna teach you guys how to add. Not even subtract. I don't think we got enough time to talk about subtraction today. Okay, so we'll talk about addition, which is this line here, this link here, adding, and also the link right below that, which is kind of interactive reading material. It talks about the concept, give you a few questions, you can answer that. It's the score of the binary adding kind of quiz does not count in the final grade. Okay, it's really just for your information. So if you decide not to answer the question, then just say, okay, give me the next slide. Hey, that's okay too. It's just that the questions will help you understand realize whether you understand the material or not. So if you ace all of the questions, then you're probably having a good idea of what the material is talking about. On the other hand, if you answer the questions and there are some answers that are wrong, you might want to find out why they are wrong, just to make sure that you understand the concepts. But once again, it doesn't count to your final grade, so as a result, it is quote-unquote optional. Okay? But reading it is not really optional because that's the material that we're going to talk about in this class. All right, so we'll start with adding, okay? And I just want you guys to kind of close your eyes and think of yourself as a 6 or 7 year old, back in those days, okay? And try to remember how you learned adding in base 10. Okay? So, let me just ask you this question then. I'm going to switch to my document camera. This is why I like a VLC, because VLC is just a really, really cool tool, useful for a variety of things. I can just use it to play the my document camera. I mean, it would play movies and stuff like that too, but this is one of the many things they can do. It can do screen capture too, just in case you don't know. VLC can do screen capture, but it cannot do screen capture with voice, and that's why I don't use it for screen capture.
So it can take the feed off your webcam? Is that basically the same thing right there?
Yeah, it's taking the feed out of my document camera, which is basically just a fancy webcam on a stand. That's basically what it is. Of course, I added this a little LED light thing. Otherwise, it doesn't really it doesn't show as well on the projector. All right. So what we're going to do is to talk about adding. Okay. So you say, okay, what is 4 plus 3? And you go like, oh, Tech, come on, this is cisp310, one of the last computer science classes you're going to take, right?
You all know it's 8.
So why are we asking this question? But how do you know the answer is 7 in base 10? I mean, how do you know? You have it memorized already. Okay, you're not counting. You're not saying, okay, 4 and then plus 3, 1, 2, 3. So the answer is 1, 2, 3, 4, 5, 6, 7. That's not what you're doing, right? You have already memorized all this stuff. Okay, so this one seems easy. Okay, so I'll ask you another question. What is 5 plus 8? I'm just picking random numbers here. Okay, so you look at 5 plus 8 and you go like, okay, 5, and then okay, 1, 2, 3, 4, 5. Uh-oh, I ran out of fingers. So I'm going to say, okay, there's a carry of 1, right? And then you start again from 0, and then 1, 2, 3, so you have 13. Is that right? Okay. So the way I'm going to write 13 is just saying it's a 3 with a carry of 1. Because this way of representing quote-unquote 13 gives me the ability to stack it so that I can perform multi-digit addition. Is that okay so far? I'm not getting any problems with addition in base 10? Okay, I'm certainly hoping not. Okay, all right. So the next thing we will talk about is what exactly is a multi-digit number. Okay, so we'll use base 10 numbers as an example. So we'll start with something like, okay, 4, 1, 6, 3. Okay, this is a base 10 number unless I specify the base otherwise. It's just assumed to be base 10 decimal. Okay, so 4, 1, 6, 3. The typical convention is the left-hand side are the more significant digits and the right-hand side are the least significant digits. Since I do not have a decimal point here, this is an integer. Is that okay? Conventional stuff, okay? But I do want to throw those terms out, okay? Most significant digit is 4, least significant digit is 3, because we will be using those terms all over and over again in this class. So I do want you guys to get familiarized with those particular terms. So 4,163, okay? So what is exactly that? It's 4,000 plus 100 plus 60 plus 3. Everybody knows that, right? Okay. If anybody feels intimidated by this, equation here, this may not be the best class. I'm only saying that half kiddingly, okay? Because really, I mean, if people are not feeling comfortable with this line of, arithmetic, this may not be the right class. Okay, so what is 4,000? 4,000 is 4 times 1,000. 100 is 1 times 100. 60 is 6 times 10, and then 3 is 3 times 1. Okay? Now the reason why I made this transformation is not really to spell out the obvious, but to try to spell out the not so obvious. Okay? Because the 4 is really the quantity of how many thousands we have. The 1 is how many hundreds we have. The 6 is how many tens we have. And then 3 is how many units or ones we have. Okay, now that is important because that aspect of how numbers represent values is universal across all bases. Okay, it's not just base 10, base 2, same way, base 4, same way, base 8, same way, base 16, same way. Okay, and then I'll go one step further and say that 1,000 is nothing more than just 10 to the power of 3. Okay, 100 is 10 to the power of 2. 10 itself is 10 to the power of 1, and 1 is 10 to the power of 0, okay? So now we start to see another pattern, right? Because 1,000, if you look at the powers of 10 that each digit is representing, it's a sequence, okay? We start from the right-hand side, which is the base, which is 10 to the power of 0, and then the next one is 10 to the power of 1, the power of 2, the power of 3, and you can kind of imagine that one's 4, 5, 6, and so on. What about the decimal point? Well, on the right-hand side of the decimal point, we go -1, -2, -3, and so on. So it is really clear at this point, I'm hoping, that every digit in a number, no matter what the base is representing the quantity of a particular power relative to the base that we are using. Is that okay? Excellent. All right, so now that we got the basic addition stuff done, okay, and we got the way we represent numbers done, both in base 10, we can start to think about how to transition to binary numbers, okay? Now, binary numbers are particularly important because of the stuff that we have already talked about, okay? Do you remember the transistors that makes a NAND 2 gate, okay? And what are the possible states of the input to that particular circuit? High or low, on or off, 0 or 1, right? But regardless, there are only 2 possible states. And when you look at the binary number, binary means each digit can be a 0 or 1, okay? So now we have a very direct mapping between the physical state of something as opposed to the quantity that we wanted to represent, okay? Which is great. And why do you think we don't have analog computers as opposed to every single thing here is not only digital, but is binary? So why don't we have analog computers? This is a little side tour. Yep.
Hard to produce.
They're hard to produce. You're exactly that's true. They're really hard to produce. And the reason why they're hard to produce is you have to select the transistors so that they're very consistent. Okay, given the same gate input of the transistor, it has to turn on the transistor exactly the same way. Okay, because it's analog. But say again.
It has to be very sensitive.
It has to be, well, not sensitive, but very reproducible, and it needs a lot of consistency between transistors. But when it's binary, you hardly need any consistency between transistors. So the gate voltage can, to switch between 0 and 1, one can be 2.5 volts, the other one can be 2.2 volts. Hey, as long as it is way above 0 or way below 5 volts, there's a big threshold, there's a big region where you can say, that counts as okay as well. Okay, so binary computers have that particular aspect, being easy to manufacture, and you don't have to have high consistency between transistors. Okay, so getting back to this picture here, I just want to make one more point. And the point has to do with how big is this table that you have to memorize as a child? In other words, how do you know that 2 plus 5 is 7? And do it like, you can memorize that, right? I mean, this is all in your memory. So how big is that table when we're talking about base 10? Well, if you think about it, okay, the base 10 table looks like this, right? 0, 1, 2, blah, 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 up to 9, 0, 1, 2, all the way up to 9. And then some people can say, but 0 plus anything is just itself. So let's not talk about this row here. It's not needed. This column is not needed either. So
that's gonna
You
be
mean 0
80?
times 0.
So 80?
no, I'm talking about plus. Oh, 0 plus whatever is whatever.
Yeah.
But the addition table is something that you have memorized already as well. Okay, so this is a table that you have already memorized. Okay, so we have the top row, not needing to be represented. The left column does not need to be represented. So now we are left with a 9 by 9 matrix. Of the 9 by 9 matrix, about half of it, not exactly half, but about half of it is symmetric, so you don't need that either. So you basically end up with a 9 by 9 divided by 2, which is not an even number, but I would say approximately 40 entries to remember, and of which probably, let me just count. About half of those have carries of 1. Okay, is that right? Yeah, I think about half has carries of 1, but that's a table that you have memorized. And if you have any younger sibling or children that you help to educate and bring up, you probably will know that this takes time. Okay, it takes a little bit of time for kids to remember, okay, and not to make a mistake and say, oh, what is 4 plus 7? It's 11. It takes time. Now to us it's easy because we have been using this for decades. Okay, but for children who are still learning, they can make mistakes because there's a lot of just memorization involved in this sort of thing. Is that making any sense? Sort of? All right. So what we'll do is we are switching to binary numbers now. All right, so binary numbers, first of all, we talk about the representation, how a binary number represents a particular value. So we'll take a look at 0, 1, 1, 0, 1, 0, 1, 1. In base 2, the subscript 2 is basically saying it's a binary number. Okay, so how do we look at this? Okay, I'm not going to go spell out the whole thing because it's very tedious with binary numbers. But this digit is representing how many ones we have. This represents how many 2 to the power of 1s, which is 2. 2 to the power of 2, 4, 8, 16, 32, 64, and 128. In other words, each digit is telling me, exactly how many powers of 2 do we have corresponding to that location. But the best part of a binary number is you either have 1 or you have none. So the best part is you don't have to do multiplication. To figure out the value that a binary number is representing, you don't need multiplication at all. Unlike a base 10 number where you need multiplication. Okay. So this number, getting back to this one, is basically 1 plus 2, which is 3, and then has no 4 and 1 8. So we got 11. This is all base 10. And then we have a 32. So we have 43 and a 64. So that adds up to 107. If you have a a calculator that is capable of binary to decimal conversion, you can double check and make sure that that really is the case. Okay, I'm fairly sure, but I make mistakes when I do arithmetics. Okay, so are there any questions about this part here? How a value is represented in base 2 as a binary number? No questions? Okay. Which is the same thing. I mean, if you want to expand this, it becomes 0 times 128 plus 1 times 64 plus 1 times 32 plus blah blah blah. But then you can say, okay, what is 128? It's 2 to the power of 7. 64 is 2 to the power of 6. 32 is 2 to the power of 5, and so on. You can see how this resembles the previous slide, where I work out a base 10 number. Are we seeing any parallel or similarity between these two slides up to this point? Is it all good? Yep.
Yes, sir. So how are you doing with addition? So if you take a 2 and 1, you've got 3, and then...
Okay, think of it this way.
Yeah.
In a binary system, let's think about dollar bills, okay? Because when it comes to money, we pay attention. Okay, so instead of having the dollar bills system that we have at this point, you have 1, 2, 4, 8, 16, $32, and so on. But you can only have one or none of those dollar bills when you pay someone, or when you have when you get your paycheck. You can either have one or none of any particular value of those bills. Okay? So when you look at this number, it basically says you have one $1 bill, one $2 bill, one $8 bill, but none of the $4 bills, and so on. Okay. All right. So any other questions about binary numbers? How they represent values? Now, what about 1.011 in base 2 with a decimal point? It works exactly the same way as decimal numbers, so you basically just go negative in terms of the power to the base that we are talking about. Since we're talking about base 2, it is 2 to the power of -1, 2 to the power of -2, and 2 to the power of -3. So let's work this out. The 1 is easy because it is just 2 to the power of 0. The 0 is representing the number of 2 to the power of -1, and then we have 1 times 2 to the power of -2, and then we have 1 times 2 to the power of -3. So this is just 1. That's 0. And for those of you who prefer SAE units and stuff like that, we can say this is 1/4, and then this is 1/8. So when you add up everything, this is 1 3/8. There we go. Or if you prefer, it's 1.375. Same thing. Is that okay? All right. So now that we know how values are represented in base 2 as opposed to base 10, let's think about how numbers are added in base 2. Okay. Can I move on from this slide, or? Okay. So there's no need to really copy everything because I double checked that I'm actually recording. So as long as we don't have any technical difficulties, everything is being recorded and it will be on YouTube. Okay. So now we'll talk about how we add numbers in base 2. So we'll start with 3 trivial cases. And once again, if we have problems with these 3 trivial cases, I think we have a big problem. None plus none is none, okay? Doesn't matter what base you're talking about, right? How about 1 plus 0?
1.
Okay, 0 plus 1? 1. Okay, so these 3 is universal. It doesn't even matter what base we are using. You can be using base 13 if you want to, and this will still work. Okay, because 1 is always 1, and 0 is always 0, regardless of the base. And because 0 is the identity of addition, when you add something to 0, you just get the other thing back. Okay, so that part is easy. So the only tricky one is 1 plus 1. And this time I have to say in base 2, because otherwise you can say, oh, it's just 2. No, but because in base 2, you cannot have a single digit representing 2. What then? Why not? Well, it's just like in base 10, do we have a single digit in base 10 that represents the quantity of 10? No, 10 is represented by 1, 0. Okay, not a single digit. So in base 2, we cannot represent 2 in a single digit. It is represented as 1, 0 in base 2. But that makes perfect sense because this 0 means we have no 1s, and this 1 means we have 1, 2 to the power of 1, which is 2. So when you add 2 plus 0, it is exactly 2. So it does make sense. But that's the only tricky one. In other words, if we were to introduce base 2 numbers instead of base 10 numbers in elementary school, addition is done in 15 minutes. I mean, seriously, we don't have all those other tricky ones to remember. The only tricky one is 1 plus 1. It is 1, 0. Are there any questions about this? Now, since I did not use this representation in the other slide, I say 1 plus 1 is 0 with a carry of 1. Same thing, just represented slightly differently, because this way I can stack the columns, so I can add multiple digits. All right. So, any questions? Because I know this stuff is, I made a really kind of subtle transition from the previous slide to this slide. I mean, the previous two slides, or two pieces of paper are really easy. You guys probably get everything. But this one, I'll just let you guys digest it a little bit and see if you have any questions. Any questions? Yep, go ahead.
I know this is not base 2, but I was wondering how would it look like in base 3?
In base 3, you do have a 2, because in base 3, every digit can be a 0, a 1, or a 2. So 1 plus 1 will still be 2. But 2 plus 1 is going to be 1, 0. Because 2 plus 1 has a quantity of 3 that we call 3 in base 10, but that quantity cannot be represented by a single digit in base 3, because each digit can only be a 0, a 1, or a 2. So it has to be a 1, 0, because the 0 is representing that you have no 1s, but that 1 is representing that you have 1 times 3 to the power of 1, which is just 3. Okay. Yep, that's a good question. Yep.
So then technically 10 is how you represent every base.
1, 0.
1, 0.
1, 0 is the value of the base itself. Yep.
So do we have NAND gates giving us our zeros and OR gates giving us our
We are getting there. Okay, we're getting there just slowly. Okay, at this point, I'm just making sure that we know how the addition table works in binary. Okay, but that's a good question. We are going to get there. Okay, we will get there. Okay, so no questions about this? This is all good? Okay. So if this is all good, then I am going to say, oh, let's look at the truth table here. Okay, I'm just making sure that the truth table is displayed on screen. Okay, so here's my truth table. It only has 4 rows, but I'm going to label these columns so that we know for sure which one is which one. X is 1 bit, Y is another bit. Okay. Okay, do you guys have any questions? Yep.
For the base 1 addition, how do you do that?
There's no such thing as base 1.
Then you would have another digit.
Well, okay, in theory you can have a base 1 because then you have the quantity of 1 to the power of 0, 1 to the power of 1, 1 to the power of 2, and so on. So that means, but you have no way to each digit has nothing other than 0, right? So you can't really have a base 1 number. So 2 is the minimum. Okay, so this one is going to be this thing here. So I'm just going to say the result of x plus y. And this one's going to be the carry of x plus y, which is this thing here. So this goes here, that goes here. X is this number, y is the other digit. There we go. So are there any questions about how I map the addition in a more traditional form to the table form? Okay, it's just, what thing in addition is x, what thing in the addition is y, what thing is called the quote-unquote result of the addition, and what thing is called the carry of the addition. Are there any questions about how the general addition format maps to the table? No questions? Okay, if there are no questions, I'm going to fill out this table. The first thing I do with any type of truth table, which means each thing can only be a true or false, a 0 or 1, is to fill it up first. Okay, now how you want to do yours is up to you, but this is typically how I do mine. The leftmost column is the one that changes the least frequently, and then the rightmost column of the independent variables is the one that goes alternate between 0s and 1s. But that's just my convention. I mean, you guys can feel free to use any convention that you want to use. Okay, so now we can fill up the rows and figure out, okay, what is the result of x plus y, which is corresponding to this one here? It's a 0. What is the carry of 0 plus 0? Do we have any carry? No. Okay. What about 0 plus 1? 0 plus 1 has a result of 1 and a carry of 0. 1 plus 0 has a result of 1 and a carry of 0. And the only tricky one is 1 plus 1, which has a result of 0, but a carry of 1. Are we doing okay so far with this particular slide? I'm just going to pull it down a little bit, so this way we can see the entire thing. So the table is no more than just summarizing everything that has been discussed already. It's just putting it into a tabular format for a really, really important reason. Okay, do we have any questions back there? Any questions?
No, I
Okay. All right. So we are good with this slide so far? Okay. So what we want to do now is look at this table or look at one particular column. Pick one. Okay. We'll pick the carry first because that's the easier column. Okay. So we look at the carry column, and I'm going to put it on the side here, on the other side here, and I'm just copying everything here. There's no need for you to do exactly the same thing. I just ruined it. X, Y, and then we have the result of x plus y. Okay, I just called it R, in parentheses xy, so I don't have to keep saying the result of x plus y. Okay, this is just a shorthand. Okay, 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, and then 1, 1, 0 here. Okay. This is the harder one. Well, shall we start with the harder one? Do you want to start with the easy one?
We already wrote it down.
Okay. So I think we should start with the easy one. So I'm going to leave this one here, and I'm going to start with the easier one, the carry one. So this is the carry of x plus y. Instead of spelling out carry of x plus y, I just called it c, and then in parentheses xy. Okay, this is the easier one because you might be able to just visually see the whole thing. Okay. And that. Okay, so let's focus on just this one. Okay. Do you think the truth table reminds you of something that you already have learned?
Yes.
And what would that be?
And.
Conjunction, and, right? Because 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is the only case where you have 1. Okay? Because when you look at 1 as true and 0 as false, that's the same thing as in the truth table of conjunction. But what is that telling you? It means a single AND gate can be used to compute the carry of binary numbers, addition. Okay? Now this is important. This is big. Okay? I'll re-emphasize why it is big. Okay? So you can basically say, hey, it's the same thing as x and y, because that would give me exactly the same values.
You're off screen.
Sorry?
You're off screen.
Oh, I'm off screen. That gets a little tricky. Maybe
I
that.
was thinking you really
Because I have to lift one side, it doesn't look square anymore. All right. So that's actually big, because do we know how to make an AND gate out of transistors? Yes, we do, because it is 2 NAND gates, right? We have one single NAND gate to perform the actual conjunction, and then the other NAND gate just to do negation. But each NAND gate it has 4 transistors. So using 8 transistors, we can now implement the computation of the carry of addition in binary. Now, I think this is big because it has just bridged, physical implementation using transistors, or if you want relays, vacuum tubes, whatever, okay, or even air valves, okay. We have just bridged physical devices to computation. Now you might say that, hey, this is not a very big thing, okay? We just learned how to do the carry of binary addition, but it's one step, okay? It is one step, and nonetheless, it bridges from the physical world to computation, into arithmetic, adding. Is that okay? All right. So the next thing we want to do is to say, but what about the other guy? What about this guy here? That looks a little bit nasty. You know, we don't have a single binary operator that can do this. Well, you are true. It is true. Okay, we have no common binary operators to do that, because you can actually define binary operators any way you want, but you know, we don't have anything that's well known that can get this done. So what we'll do is we'll say this is the result of x plus y. Okay, so same table, I'm just copying everything to the new sheet of paper. Okay, so nothing really big important here. Okay, 0, 1, 1, 0. So what I want to do is to say, okay, if I can only use negation, conjunction, and disjunction, is there a way to use an expression here that will give me exactly the same values as r, x, y? That's the question. Okay. Now there are several ways to do it, so you know, you can pick any one of those ways. So I'm going to give you guys about 5 minutes to kind of work on your own to try to come up with an answer. Okay, and then I'll give you, one of my answers. Okay, because there are multiple correct answers.
And you're looking for a sequence of just negations and conjunction disjunctions that will create.
Correct. Yeah. So in this space here, just use negation, conjunction, and disjunction, and then use x, y. But you can use parentheses of any level, any type of nesting, and stuff like that. Okay. All right. Well, for those of you who can think in NAND, you can think natively in NAND if you want. I cannot. So I'll give you about 5 minutes to do this. So I'll check with you guys at 9:40. It's 9:36 right now. I mean, during this time, you guys can chat with each other if you want to. I mean, it's fine. That's part of the whole thing.
What I got is it's either x not y or y not x. If it's both of them are neither, then that's false. And if both of them are true, then
Oh, note that exclusive OR is not something that you can use, because that will make it too easy.
too obvious.
Wait, what?
Because that's what that is. It's an exclusive.
Oh, that's not what we're doing.
No. I mean, that's what he wants, but that's what you just basically wrote down as an exclusive. So you did it right. No.
But I did it the easy way.
No, that's not the easy way. The easy way is you just write next one. That'd be the easy way.
But since you can only use these
Exactly.
three
You did it the right
operators,
way. So you did it
Okay.
right. Yeah, the easy way is 3 letters.
I wonder if you can use an AND gate.
Are you? I mean, because.
you need AND gates for this.
Do?
Yep.
Oh wait, so when you said you don't have an operator here though, you have x not y, so you're just taking it as x and not y.
Oh yeah.
Yeah, I think in most implementations you need an AND gate, but there are multiple ways to express it.
So C doesn't have. C doesn't have an exclusive or does it?
It has a bitwise exclusive OR, which is known as a caret. Yeah.
So how deep is logic? It's that. That's what you have to do.
I should have started my Pokemon Go, so now I get time to throw a few balls and collect a few things.
They took.
I think we're close enough to
addition,
pick up
finding this out.
those two stops.
And they've made everything.
Oh yeah.
No, that side.
From one building block.
And created the world. Not the
Yeah.
world. I mean,
The world of computers.
Yeah.
From one building block.
Wait, so there have been actual mechanical computers? Because the only one that I know about is the difference.
The mechanical computers are not binary. They use base 10. There's one in the Computer Museum in Santa Clara.
And what is it all out of?
It's a computer designed for one specific purpose. So it is a computer, but it's not like a programmable type of computer.
What is it? What's that purpose?
I cannot remember. I just know that it's really heavy. It has got cogs, gears, and stuff like that. It was donated because the guy who bought it did not have sufficient floor support to put it in his living room.
Support? like in his living room. I mean, that's crazy if it was on the, especially if it's like
It's gigantic.
If your living room is on the floor.
What do you think about quantum computing?
I don't know a whole lot about that. I just know that it's based on quantum phenomena.
Do you think it's possible?
I think it is. I think it is. It's just a matter of getting the right material to do it.
I tried to watch like For Dummies, and it's like
Even for dummies, it's like you're a smart dummy.
yeah, it explains something like it could be in between 0 and 1, and I don't understand how that's possible.
Right. Well, okay. So I think it's about time. It's 9:40. So we have about 4 or 5 minutes. Okay. So the key to do this is to look at the values when they're ones, and then you just say, okay, how can I take care of that one, just that row? Okay. So we'll use that technique here. So forget all the zeros. I'm not too concerned about the zeros of the third column. I'm only concerned about the ones of the third column. So if you focus on just this one here, okay. This one is a 1 when x is a 0 and y is a 1. So if I don't have to worry about anything else, just to take care of this column, one way to confirm that I only get a 1 when x is 0 and y is a 1 is this equation here. Okay, you just basically say not x and y. Right? That one single expression, not x and y, will take care of the second row because for everything else it's going to be a 0, but only for the second row it'll be a 1. Are we doing okay so far with that method? Okay. But what about the other one? Well, let's work it out. Okay, the other one is here, and so if you use the same method, this one requires x to be a 1 and y to be a 0, so we have to negate the y. So the second expression is going to take care of the third row over here. So I'll just draw some arrows here. So we will say this takes care of that. This takes care of that. Okay? But tech, we want the second row to be a 1, even though we have the second component. We want the third row to be a 1 despite the first component. Well, that's easy to take care of. All you have to do is to put an OR here. That's OR. That's regular OR. That's just regular OR. There's no exclusive OR operator in logical exclusive OR operator in C and C++. Okay. So when I propose solutions like this, those of you who have taken classes from me know what I'm going to ask next. Do you trust me? Now, the obvious answer is you should not, okay? Because if it's something that you can verify and validate independently, you should do that, okay? All right, so what we'll do is we'll double check, okay? We'll double check and say, okay, on the first row, x is a 0, not x is 1, y is a 0, but with a conjunction, if any one side is a 0, the whole thing is a 0. So the first expression is a 0. The second one, I can use the same argument because x is already a 0. I don't even need to look at y. The second expression, the second conjunction expression is also a 0. 0 or 0 is a 0. Okay? There we go. There goes the first one. Second row, we have x being 0, not x is 1, y being a 1. So we have 1 and 1. So one side of the disjunction is a 1 to begin with. With the disjunction, if at least one side is a 1, the whole thing is a 1. So the whole thing is a 1. I can do lazy evaluation. On the third row, x is a 1, not x is a 0. 0 and whatever is always a 0, so I don't have to evaluate the rest of the first conjunction. I now look at the second conjunction. x is a 1, y is a 0, not y is a 1. So we have 1 and 1. 1 and 1 is 1, and so the entire disjunction has a result of 1. And then on the last row, we have 1 for x and 1 for y. If x is 1, not x is going to be a 0, 0, and whatever is always a 0, the left-hand side is always a 0. And we can apply the same logic to the right-hand side, because x is a 1, but y is also a 1, not y is going to be a 0. Anything and 0 is a 0. So now we have 0 or 0, which means the whole thing is a 0. Okay? Is that okay or not? Yes? Okay? All right. But you should always kind of double check and validate the answers that I propose, especially when it is kind of easy to do it. Okay? Maybe a little tedious, okay? But it's a good exercise to do it. Okay. But what is this getting us? Oh, it's making that connection again, right? Did we talk about how to do negation using a NAND 2 gate? Did we talk about how to use a NAND 2 gate to implement regular AND, A-N-D? Did we talk about how to make OR gate out of NAND 2? We did. Well, guess what? This thing is a little bit complicated, but it only makes use of NOT and OR. And we already know all of those gates can be implemented using just NAND 2 gates. Now, what about NAND 2 gates? Why do we keep getting back to NAND 2 gates? Why do I have an obsession with NAND 2?
The simplest gates to make?
Well, it may not be the simplest, but we have shown that we can use 4 transistors, 2 p-channel MOSFETs and 2 n-channel MOSFETs to make a NAND 2 gate. So what this is saying is, now we have a way, although it may be clumsy and not optimal, but we do have a way to make, to implement addition, arithmetic addition, using transistors. So the significance is now we have a way to go from physical devices to actual arithmetic calculations. Okay. Now I'm not sure about you, but to me, as I teach this class, more and more, this sort of thing just it just blows my mind. Okay, because now we have made that connection. It's very simple, and every single step seems to be fairly, easy and natural. But in the end, now we know how to make the most basic components of a computer. Yes.
So ideally, we could rig up that NAND 2 gate in real life and do simple mathematics like this.
Correct. We just need a whole lot of transistors. And guess what? Your processor has a whole lot of transistors, right? Millions and millions of transistors. But that is the significance. That's the significance of what we have talked about so far. Is we are now capable of going from physical devices to a structure of those devices to actually perform addition. You might say it's only adding 2 bits. Okay, what is the big deal? Because if we can add 2 bits, we can add any number of bits, because we can just use the carry to push it out. Okay. All right. So now we are defining something like this: the carry of addition between x and y, x being 1 bit, y being 1 bit. This is from the previous slide. You don't have to rewrite it. It's just x, y. This is because x, y is the same thing as x and y. It's just a better way to express it. It's typically used in electrical engineering and computer engineering. They do not spell out, the and. Okay, they certainly do not use ampersand, ampersand. They just say x times y. So, quote unquote, multiplication is kind of the same thing as conjunction or and when it comes to the use of symbols. Okay, so I'm just kind of give you guys or introduce you to multiple representation of the same thing. Because depending on which college you go to, you might need to know all of these representations. All right, so this is one. The result of adding x to y is this thing here. Okay, so I'm going to give you an alternative expression that is easier to just write down. So it is x bar y plus x y bar. Okay, so the bar is a negation. And then the addition, quote unquote addition, is disjunction. And you can see how compact this expression is compared to the C notation up here. Is that okay so far? So remember, in the shorthand notation used by mostly electrical and computer engineers, addition means disjunction, and then multiplication means conjunction. When you need to negate, you put a bar on top of whatever you're negating. Is that okay?
Addition is disjunction.
Addition is disjunction, because it is really kind of similar.
I mean, I'm only seeing that like, it now makes sense because it's the operation that gets us the addition, or the results from an addition.
Well, not quite that, but in terms of algebra, it carries the same properties when it comes to identity, because in both cases, whether you're dealing with addition or disjunction, false or zero is the identity. When it comes to multiplication or conjunction, 1 is the identity. So from the perspective of abstract algebra, the symbols are consistent between those two systems.
It's just the English, because like addition plus is addition, which
Yeah, so this one is really an or, and this one is really a and this is a not. Okay. All right. So, are we doing okay so far? Are there any questions that you want to ask about all this stuff at this point? No questions? Sorry, go ahead.
No, I just don't know how to put it in words. So the second one over there, x, y, and then x and %y.
You mean this here?
No. It's on the right. Yeah.
This one here?
Yeah. What does it say?
It's just a symbolic equivalence. So in C and C++, ampersand is conjunction.
Right.
But in electrical engineering and computer engineering, x times y also means conjunction.
Okay.
It's just a shorthand because we don't like to type ampersand.
Okay.
Of course, if you're using Notepad to type this, there's no way to put a bar on top of something.
Right.
Then you use a slash. Okay, so this is also known as slash xy plus x slash y. The slash is negating whatever is after that. So this way you can actually use Notepad to express it. Oops, you cannot see that part. There we go. Okay. Okay, any other questions before we proceed? Because the next thing we're going to talk about is we'll go ahead and try out a few actual binary addition so that we can understand these are really, really basic components, and we want to see how they actually apply in a circuitry. Are we okay to go forward, or do you guys need a little bit more time here? Ready? Okay, let's go. I'm really liking this document camera thing. I mean, it's not like the notes that I have on Moodle is useless, but this is more interactive, kind of live. And I get to kill a few trees in the process. Yes. Okay. So now let's go ahead and just apply what we have learned and perform a few actual addition in binary. Okay. So we'll start with let's try 1011 plus 0010. Okay. And these are base 2 numbers. I just want to emphasize, do not apply the base 10 rules and use the base 2. Okay. So the way I do this is I have one extra row. This row is just for carries. Okay. I just like to spell it out. Okay. You can kind of do it whatever you want, but I want to spell out the carries of the addition of the column to the right-hand side. Okay. All right. This 0 is here because this column is already the least significant digit. There's nobody contributing a carry to this column, so the quote-unquote carry is always a 0. But I would like to spell it out, okay, just so that we know, oh, there is a carry, it's just a constant 0. So the first thing we do is we perform this addition. 1 plus 0 is 1. Does it have a carry? No. So if it doesn't have a carry, I'm not going to put a carry here. And then we have a second addition, which is 1 plus 0. Does it have a carry?
Yes.
1 plus 0 does not have a carry. It has a result of 1. Now, because neither addition, this addition does not have a carry, this addition does not have a carry either, so there's no carry overall in the next column. Is that making any sense? It's the same way in base 10, okay? We are not doing anything really that differently compared to base 10. Okay, so up to the second column, we have 1 plus 1, which is a 0 with a carry of 1. If you know there's a carry, just write it here. Okay? What about this 0 plus 0? What is the result of 0 plus 0? It's just a 0. Okay, very good. Now we have 0 plus 0, which is a 0. Does it have a carry? No. Okay. 0 plus 1 is
1.
a 1. Does it have a carry? No. So once again, this addition has no carry. This addition has no carry, so the overall carry is 0 to the next column. And the last column is 1 plus 0. What is 1? It's 1. Has no carry. 1 plus 0, once again, is 1 with no carry. So even though normally we don't really represent the carry after the most significant digits, in binary addition, it is important, so we keep track of that. Do we have any questions about this binary addition operation? Yep.
So is there like a purpose to the third line, the 1001? Is there like a purpose to it? So I was able to do like the math now.
There is a purpose to that because in the circuitry to represent an adder, that represents the interface between certain components, and that's why I spell it out. Okay, so I claim this answer is correct. What do you do?
Never check it.
You check it. How do you check this? What is one quick way to check it?
Binary calculator.
Oh. Yep, exactly. Pull out your binary calculator, or your phone for these days, because your phone can have any type of calculator installed. You cannot use that in an exam, so you have to really use a calculator. But in class, just for convenience, you can use any calculators. Yes.
You could also calculate the first number, calculate the second number.
Yeah.
In base 10.
Yeah,
In
convert
base
it to
10,
10 and then-
So 1011 in base 10 is 11, and 10 is 2. So when you add these, it's 13. So now we want to ask the question: is this really 13? We got 1 1, we got 1 4, and we got 1 8. 8 plus 4 plus 1 is 13. So unless I make two mistakes and they kind of cancel out each other, it seems correct to me. Okay, that's as far as I will say as far as correctness. Okay, yeah, go ahead.
If we had done 1011 plus 0011 instead, and we add the
Well, let's do it.
I want to see how that looks.
Okay, what again?
1011 plus 0011.
1 0.
That bottom basically the addition that's there underneath the main one.
So we're talking about double carry.
The one in the middle.
The one in the middle.
Yeah.
You mean these two?
Yeah, those two. Yeah, right.
No, instead of doing 0010,
Uh-huh.
the second row you do 0011.
0 0 1 1. Okay, so you still have this and then 0 0 1 1 here.
Yes.
Okay, well let's do that. Okay, so once again, I explicitly spell out the carry of each column because it is important to understand that part, especially when we try to convert this into a circuitry. Okay, so I'm going to do this one a little bit faster now, okay? 1 plus 1 is a 0 with a carry. 0 plus 0 is a 0. 1 plus 1 is a 0 with a carry. 0 plus 1 is a 1. 0 plus 0 is a 0. 0 plus 1 is 1 with no carry. Neither produces a carry. And then we have 1 plus 1, which is a 1. 1 plus 1 is a 1 with no carry. Okay. So according to this addition, just spelling out, saying out loud, the rules, the end result is 1 1 1 0. So we want to double check. Okay. So this is 11. That is 3. So the end result should be 14. And we have no ones. We have 1 2 1 4 and 1 8. 8 plus 4 plus 2 is in fact 14. So once again, unless I make two mistakes and they mask each other, this seems to be correct. Now, don't laugh, okay? There are cases where we can make two mistakes, and they mask out each other. In other words, the second mistake will make the first mistake invisible. That happens a lot in programming. Okay, you can have two bugs. One bug is hiding the other bug, so your program seems to be working correctly.
It's called features.
There will be a KB entry for that later on. Yes.
Then they fix it and the other bug shows up.
Okay, so are we getting a little bit comfortable with binary addition, or do you guys want more examples? It's good. Okay.
So in the middle one, the top can be viewed as a result, and the second one could be viewed as a carry. You get what I'm saying?
You mean the rows?
Yeah.
Yeah, this is basically the C of these two, and that's basically the R of these two, and then this is the R of these two. So the
we're adding twice.
Yep. Every column has actually two additions, but it's the same way with base 10. If you think about base 10, it's really the same way.
And the second one is guaranteed not to have.
They cannot both have a carry of 1.
Yeah.
I think that's what you're asking, and the answer is yes. They cannot both have 1s. Go ahead.
So what about 1111 plus 0001?
Okay. Well, we'll take a look. Okay.
All
So
ones on the top and then all.
I'm going to pass the row sheet at this point because I tend to forget, and this will help with it. Row sheet. Okay.
No, all ones. Yeah, all ones would be.
Okay, so we'll do that one. Okay, 1111 plus 0001. Okay, it's interesting and boring all at the same time. It's one of those things.
Oh,
Or I
see,
should say
you
the
could do
first part is
overflow.
really exciting, and then the rest of it is like kind of like the latest Avenger movie. Yeah. The opening is like, oh, that's cool, and then after 15 minutes, it's like, oh. And then you watch Deadpool.
It's all good.
It's all good, exactly, all the way to the end. All right, so we'll do this one, and all right. So I'm gonna do this quick, okay? 1 plus 1 is a 0 with a carry. 0 plus 0 is a 0. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. This is where it all goes downhill and gets really boring. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. 1 plus 0 is a 1. 1 plus 1 is 0 with a carry.
And that's where
That's it.
zero.
Then you got to bring that one down.
No,
What?
you don't have any bits.
You don't have any bits left. We're talking about 4-bit adding. So the result is actually saying that 15 plus 1 is 0.
So we got a bit overflow.
No, we don't call it overflow. This is called, you just have an extra carry, that's all.
So is there a way to record that extra carry somewhere?
Yes, that carry is not stored as the result, but yet it is registered somewhere. So the processor actually knows, oh, there's one extra carry of 1 out of the last addition.
So what does it do with it?
Comparing, it depends on what you're doing. Okay, it depends on what you're doing, but it does remember that extra carry. Yep.
I'm just being stupid. So in the world where our monetary system works like this,
Sorry.
in a world where our monetary system's like this,
Okay.
and your change is supposed to be that, does a register not give you anything back? They tell you your change is zero. Like, so if you're, if we don't have a $16 unit, no. Right, like the example that you gave with the adding, where we have a $1 note, a $2 note. And this comes about, in the computer, we can store that. But in the register,
What this is representing in case of, it's basically saying, okay, I need to give you $32, but I'm out, but I don't have any $32, so I owe you $32.
So it'd
in
be
the
still
end.
great.
That's what the carry really means. So I'm going to give you 0, but at the same time, I remember that I owe you $32 because I don't have a $32 bill. Yep.
Wait, so on the second row when we're adding, if there's a carry, we move it to the next?
On the second row, you
Because
mean?
I see how we carry the first one, but how do we carry the other ones?
They
Okay.
down below.
This contributes to this. This contributes to this.
Oh, okay, there we go.
This contributes to this, and this contributes to that.
Okay, that's what I meant.
Okay, well these are all very good questions, because the next slide is going to show you, okay, what if I just name these in individual bits A, B, C, and D, and so on, how do we express, all of this stuff here using just R and C, okay, the R function for the result and then the C function for the carry. Okay, so I'm going to need a brand new slide here because it's going to be ugly. Okay, so I need to know where's the rightmost portion I can write. So I'm going to experiment here, about here. Okay, so there we go. So this is D. Okay, so we have A, B, C, D, E, F, G, H. Okay, so this is H here. Okay, and this is an addition. I'm leaving that much space, yes. Because it needs that much space. Alright, so there's a 0 here. Okay, so now I'm using letters to represent each bit. I'm not even telling you whether it's a 0 or 1. I'm just saying that D and H are the least significant bits of the two numbers that I'm adding. Is that part okay? Okay, because I want to figure out the equations. Okay, I don't want to do it by hand anymore. I want to figure out the equation, so then later on I can figure out the gate structure to get this done. Okay, so D is a bit, H is a bit, both are least significant digits. So tell me what should go here using the function that we have defined. Yep.
Both of
It's
them.
going to be R, D, H.
Yep. R, D, H should go here. And R, D, H should go here too, because we are just adding something to 0. Okay, so that's easy. But what should go here? What is the carry? CDH. Okay, very good. CDH goes here. Okay, that it doesn't seem that that difficult. Okay, this seems to be relatively easy. Okay, so now we have bit C, which is more significant compared to D, and then what is before H? A, B, C, D, E, F, G, H. Just G is here. Okay, so what should go here?
RCG.
RCG. Yep. So RCG goes here. And what should go here? No.
R.
Oh, what is the addition of, it's R of
Addition
RCG?
R of RCG and CDH.
Correct. So it's nested, right?
That's why he said it was going to be ugly.
Yes.
Yeah.
As you can see, I probably don't have enough space for the most significant bit.
These are 3 good.
I might be able to get to the bit 2, which is the third bit from the right-hand side, but that's about all I can get to.
So it's the result of the result plus the carry.
Correct.
So then,
Yes.
so then the carry of that is the carry of the result of CD and the carry of DH.
That's correct. Okay. So the bit that has to go here, okay, can be the contribution of adding these two or adding these two. So as you can see, the expression is going to be really ugly because, okay, so I'm going to pull this out and say on the side here because it is, okay, so the first contributor is adding C and G, so it's just C, lowercase c, and G. That's the easy one. But the second contributor is a little bit more complex because it is the carry of adding this and this. So to write it out, it is the carry of adding RCG and CDH. CDH. Like that. Okay. So both of these can be contributing, but I cannot just say it can be coming from here or it can be coming from there. So I need to connect these two with a logical operator. So what logical operator should I use? Or, yep. Okay. So this entire thing goes here. That's all I'm gonna say goes there. You want to go switch back to C operators?
No, just for like the ors, man. It's like
Oh, because the plus.
yeah,
makes
so
it-
it makes me think the wrong thing.
Like I said,
and
the
like I have to
English.
keep reminding myself.
The English
Fine.
messes it up.
Yeah, translate.
Now it looks like you said all.
Oh,
Okay. So are we ready to move on to the next bit? Yep. Okay. So you can kind of imagine what happens with this bit here. This is bit B from the first number. And what goes before G? F? Okay. So BF is here. This is always the easy one because it's just a result of adding B and F in this case. So RBF is this one. And this one here is going to be really complicated already. So, so what I'll do is I'm going to cheat, okay? So I'm going to say this one, I'll just call this C.
And you're off screen.
C underscript 2. Oh, sorry. I'll call this C underscript 2 because C underscript 0 is the least significant one. So this is C underscript 2 because 0, 1, 2. Okay? That's why it is called C2. Is that okay? Oh, I forgot to write the result for this one yet. Oh, no. Okay, we're good. We're good. Okay, so that's what we're working on right now. So given that I give this entire expression a really simple name, C2, now it gets a little bit easier because it's just R and then BF, right? And then on top of that, we have another R and then use C2 as the second component. But remember, it looks clean because we're just using C2, but C2 is really this junk here. Okay? But are we getting the general idea of how to structure this thing?
What are we structuring?
That whole thing, it was easier with zeros and ones, but now we're just
Right.
just to show what it actually is.
Okay, so we'll work out the most significant bit of a 4-bit number. So we have A and E over here. So this is always easy, RAE, right? So this carry can either be contributed by this addition, which is the easy part, or this addition here, which is the kind of clumsy and long part. So if I pull this out, okay, just about, okay. So if I pull this out here, this this bit here is CBF, right? Because it can be coming from this addition or coming from this addition, which is C, the carry of adding RFBF. But we already named this as C2, so that means we can just use C2 here. But remember, C2 is really a big chunk of stuff. Oh, you cannot. No, you can see the whole thing. Yep. So are we doing okay so far with this? Sort of. But do you understand? But do you see how we structure the equations, the expressions? Because that's the most important part. Yep.
It's kind of on topic. That is reminding you if you're gonna still do hacking support.
I'll do that during the lab hour. Yep, because I'm moving all the actual demonstration to the lab hour, so I will do that in the lab hour. Okay. All right. So you can see how a 32-bit adder can be a little bit hairy. Okay. Okay, but there is a way to express this, in a much more easy way. Okay. So let me just switch back here. Go to the next slide. So we'll use a notation so that it's easier, okay? So we'll just call the first number x3, x2, x1, x0. In other words, the subscript indicates the bit position, okay? The second number is y, but we will use the subscript as well to indicate the bit positions, okay? There we go. So now we have this one. This is easy to express now because it really is just x0, y0 here, and then the rest is really the same thing. I don't need to, I don't really need to spell it out. This one is 0, so this is just and we'll name the results. Okay, so I will call this R0, which means it is the bit 0 of the result. Okay, and I'll call these. I'll have names to refer to these things: C1, C2, C3, R1. R2, R3. And then the intermediate terms, you already know the pattern, okay? Are we doing okay so far with just the notation? What symbol I use to represent what part of the addition? Okay? So given this systematic way of naming the individual bits, other than bit C1, what is C I? Okay, so assume I is 2 or more. Okay, do we have a general way to express C underscript I?
Yeah, it would be either the result of.
So it's going to be C
Oh yeah,
of X I minus 1, Y I minus 1, right? It's adding the 2 bits from the previous column, the 2 input bits from the previous column. That's one contributor of the carry. What about the other contributor? Or the carry of the result of adding X underscript I minus 1, Y underscript I minus 1, and the carry of that column, which already it has a name of C I minus 1, just like that. Oh, now that looks a lot cleaner, right? I mean, that looks reasonable. We can do this, right? What about the R bits, the results? Okay, so let's take a look at Ri. And once again, we are looking at Ri where I is at least 1, okay? Because R0 is an exception case. So when you look at Ri, it's really just the result of adding, yeah. So it's R of R, Xi, Yi, right? And then the other part is just going to be this one here, which is well, that's R, and then it's Ci, yeah, and then Ci over here, and that's it. Is that okay? Is that okay? Cool. All right. So then on the next slide, well, I can do it on the same slide. Just have to kind of scoot over everything a little bit here. Okay. So I want to show the equation while I work on the symbolic representation. So what if I give you a box? Okay, here's a box. It has 2 inputs, X, Y are inputs. So I'm just going to say input, input. And it has 2 outputs. One output is R, one output is C. I like that comment. Because now that we know the general structure of this thing, if I give you boxes like that, and I say you can make as many boxes like that as you want. Now we know how to hook up things, right? Because now we can just say for each column, it really looks like this. Okay, we'll just pick this column as an example. Okay, so we'll just take a look at this column and say, how do we make this column happen? Okay, so X2, Y2 serving as input. You don't really have a choice about that because that's the actual input, and you don't have a choice of, there's no way to arrange it in any other way. Okay, so what about this part here? Okay, so when you look at the general equation, there's one more box down here. Okay, so the R of this is going into one, whoops, let me take it back. It's going into one of the inputs, to cross this out. What about the other input to the second adder? It's the carry from the previous one, right? So this is actually coming from the carry, and we label that carry as C1. Is that okay?
That would be X1.
Yes, it's the output of this box here. So you cannot see it because I'm already out of space here. Okay, but the result of this, okay, the R is, this is really R2, right? Without a D2. I can see half the class is not really paying attention. Okay, but here comes the next one. Okay, what do you think is this going to? It's another character in Star Wars. Yeah. But this is C3PO, so we have to transpose some stuff in the middle. Okay, because this really becomes C3, which feeds into the next column. But every column is going to look like that. Is that okay? So now you can have an adder that can add as many bits as you want because you just keep stamping out these things and arrange it in this particular structure. You can just keep adding it. If you want a 64-bit adder, hey, you just stack these things up. So you would end up with a 64-bit adder. You end up with 128 of these little boxes, okay? Or they're about, because bit 0 doesn't need the second one, so you can save that one and end up with 127 of these boxes for a 64-bit adder. And there are specific names for these boxes because each one doesn't quite finish an entire column. It is called a half adder. Okay, so 2 half adders contribute to 1 single full adder. I actually made a mistake. Excuse me, I made a mistake here. Nobody spotted. This C actually goes out. It doesn't go in here, and it joins with the other one using an OR. Okay, sorry about this. I know it looks ugly. And then this R actually goes in here. Okay, let me just redraw that and we'll call it a day because the next professor is going to come in and say, Tag, you need to vacate. Okay, so I'm just going to redraw this a little bit. We got XY, CR, XY, CR. The R goes into one of the input. The C of the previous one go to the other input here. So that's, and then the C of this one goes to an OR gate, and the C over here goes into the other end of the OR gate, and that serves as the C for the next bit. So that's the structure. It's all in the notes, okay? So this is nothing, everything that I talked about today are in the notes already. It's just that in the live discussion, you guys get a chance to ask questions and stuff like that.
This makes more sense. Yeah.
Okay, so you guys can take a short break. We'll be in room 128, and then I'll show you how to hack the program, okay?
The ending part, like the last
40 minutes.
Yeah.